In this lab, I wrote a program to model the path of a spring oscillating in 2 dimensions. The program predicted the path itself accurately, but seems to lag one time step behind. The results of this lab showed that the change in energy between time steps is zero, meaning that the law of conservation of energy held true. The fundamental physics principle observed was the conservation of energy. This principle states that the energy of an isolated system cannot change. The system I observed focuses on the block and includes the spring and earth. None of the energy in this system comes from external sources. The energies I observed are gravitational potential energy between the block and earth, kinetic energy caused by the block's movement, and spring potential energy from the spring being attached to a block. The concept of work, which is the transfer of energy in a system, is the integral of force with respect to a distance. Thus, the equation for energies can be derived using this principle. The gravitational potential energy is quantified by the product of the mass g and the height. Since the system is relatively near the Earth's surface, I am able to use this simplified expression for the gravitational energy. Height can be defined specific to a system. One can set some imaginary boundary so that anything higher has some positive gravitational energy and anything lower has some negative gravitational energy. In this lab, I defined height as the y position of the mass shifted up by its stretched length. The simplification mgh comes from integrating the expression for gravitational force, mg, with respect to distance, hence the h. The kinetic energy is represented by half of the mass multiplied by the magnitude of the velocity squared. The spring potential energy is half of the spring constant times s squared, where s is the distance of the block from the relaxed length. This equation comes from integrating the spring force Ks with respect to s, the distance from its relaxed length. The program itself works by using these energy principles to calculate and graph the total energies at each time step and the changes in total energies between time steps. Another window is used to display the path of the spring mass as it oscillates, both as observed in a video and as the program models. The forces acting on the spring mass are from gravity and the spring. To model the motion, I use the net force to determine and display changes in velocity and position within each time step. I initialize this program with given data. The spring constant K is 6.83 newtons per meter. The relaxed length of the spring is 0.123 meters. The mass of the weight is 0.402 kilograms, and one time step is 1/210th of a second. I found the spring's initial position vector to be negative 0.102, negative 0.607, 0 meters by using tracker. I used tracker to analyze the xy coordinates of the spring mass's center of mass in each frame. Since the object moved in an elliptical fashion, I decided to align the positive x and y axes with the right and top of the screen respectively. In the first frame, I set the stretched spring length of 0.7 meters, which was given as the scale. In the resulting graphs, the total energy is aligned with the y equals 0. Meaning that between time steps there is no change in total energy. However, the specific changes in energies oscillate. The two changes in potential energies, spring and gravitational, have destructive interference with different amplitudes. The change in kinetic energy has a shorter period than the potential energies and a smaller amplitude, which seems to counter the difference in potential energies, thus making the total energy stay constant at 0. Because of conservation of energy, we expected no change in total energy, and the sum of all components of energy equaled 0, so the energy principle was satisfied. The path of the modeled and observed spring masses were reasonably distinct. It seemed that the modeled path of the spring lagged almost an entire time step behind observed. Some difference makes sense because additional hindrance forces exist in the real world that I did not model. However, it appears that there might be some error in the model, and the observed data because they had different time steps. The period of a spring is the amount of time in seconds between oscillations. Since the spring oscillates in both x and y directions, the period can be found by using either the x versus t or y versus t plots. Using x data, I found the period to be 1.33 seconds, and using y data, I found the period to be 1.52 seconds. Although the periods are reasonably distinct, this makes sense because different forces act in the x and y directions. In this experiment, we see the energy principle and law of conservation of energy being satisfied even as the potential and kinetic energies fluctuate.